Imagine Earth before time itself decided to show up to work. No ticking clocks, no calendars, not even a fossilized footprint to whisper, "I was here." This was the age before history, before memories, before Earth even knew how to tell a story. Picture a newborn planet, molten, moody, and spinning too fast for anyone to care about birthdays. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift toward sleep, consider subscribing, only if you enjoy these calm journeys through the universe. Now, let's begin. If you could somehow stand in the nothingness of space 4.5 billion years ago and watch this molten baby Earth form, you wouldn't see the calm blue marble we know. You'd see chaos on shuffle. Clouds of dust and gas swirling in a cosmic soup so thick that sunlight couldn't even decide where to land. Time, at least the kind that leaves records, hadn't begun yet. There were no fossils, no rocks with stories etched in them, no layers to count like rings in a tree. It was a blank slate smeared with fire. We humans are obsessed with time, seconds, hours, ages, but in this era, time was meaningless. Not because it didn't exist, but because nothing durable existed to keep track of it. Imagine trying to measure time on a planet that couldn't hold still long enough to form a rock. Every second, somewhere, molten rivers shifted. New craters appeared, and pieces of crust melted back into oblivion. If there were a clock, it would have melted before its first tick. This was Earth in its earliest, most temperamental phase. The planet wasn't even fully formed yet. It was still growing, pulling in stray material left over from the birth of the sun. The universe, just 9 billion years into its life, was running a grand recycling program. Tiny particles collided, merged, and grew. It was a violent kind of teamwork. Every collision added mass. Every crash generated heat. By the time Earth had gathered enough material to call itself a planet, it was glowing with internal fury, like a cosmic ember that refused to die out. The air, if you could call it that, was nothing like what we breathe. There were no fluffy clouds drifting lazily across blue skies. There was no blue sky period. Instead, the atmosphere was thick with vaporized rock, ash, and gases belched out by constant bombardments. Space rocks the size of mountains slammed into the surface so often that if you blinked, and somehow survived, you'd miss a few hundred impacts. Earth's skin was constantly shredded and remade, a planet without a memory. It's funny to think that the same planet that now worries about daylight saving time once had no daylight worth saving. The sun's rays barely penetrated the smoky haze. From space, Earth probably looked like a glowing orange marble wrapped in stormy gray. There was no up or down, no sunrise or a sunset, just endless twilight over oceans of magma. It was the ultimate lava lamp, beautiful, deadly, and completely unpredictable. If there had been a soundtrack, it would have been pure percussion. The thunder of collisions, the hiss of steam, the roar of gases escaping through volcanic vents. Every moment was an explosion of creation. The crust, if it dared form, was constantly broken apart again. The energy released during this period was unimaginable. Each meteor impact delivered more power than all the nuclear bombs humans have ever built combined. Over and over, the planet was melted, reshaped, and reborn. But amid the destruction, there was progress. The chaos wasn't meaningless. It was sculpting the foundation for everything that would come after. Iron and nickel began sinking toward the center, forming a dense metallic core. Silicates floated upward, preparing to one day become crust. The seeds of the planet's structure were forming even as its surface burned. If you could freeze time in this era, you'd catch Earth mid-metamorphosis, like a caterpillar cocooned in magma. And yet, even in this infernal phase, there was beauty. Not the kind we'd recognize, but a raw, cosmic beauty. Think of a horizon glowing red with molten rock, of lightning flashing across volcanic clouds, of rivers of liquid metal snaking beneath a vaporous sky. It was a world alive with energy, pulsing like the heart of a star. The air shimmered with heat, the surface rolled with fire, and gravity, newly claimed, clung to it all, saying, "You're mine now." It's easy to forget that this nightmare landscape was the start of everything. Every mountain, ocean, and molecule of life we know began here, forged in the fire of a planet that didn't yet know peace. Time may not have left a trace, but the planet was already writing its preface in motion and heat. If a narrator had been there to describe it, they might have said, "In the beginning, there was chaos, and chaos had ambition." The molten tides that roared across the planet were not random. They were destiny at work. The foundations of continents, the chemistry of oceans, even the magnetic field that would one day shield life, all of it was being set in motion in this furious, formless era. So when we talk about before time, we don't mean before clocks or calendars. We mean before permanence. Before anything could hold a mark. Before a single rock could whisper to the future. This was a planet that didn't just exist in time. It made time possible by cooling, solidifying, and giving the universe a place to measure moments against. The irony? Out of all that chaos, order was quietly assembling. Out of all that destruction, stability was forming. Earth didn't need time to start its story. It needed heat, gravity, and a lot of patience. In a universe of endless noise, this young world was already beginning to hum a tune that would, billions of years later, become the rhythm of life itself. If you've ever seen footage of a volcanic eruption and thought, "Wow, that's intense," imagine that. But everywhere. Early Earth wasn't a planet with volcanoes. It was a volcano. The entire surface churned and boiled like soup on a cosmic stove turned to maximum. Rivers of molten rock sloshed around the planet's skinless body, and the air was a cocktail of choking gases: methane, carbon dioxide, hydrogen sulfide. Basically, the universe's idea of a chemical prank. It was not a place for quiet reflection, unless you counted the reflection of lava in the lava. There were no continents, no oceans, no firm land to stand on. If you somehow tried to visit, your shoes and your atoms would evaporate before you could say, "Bad vacation." The ground didn't exist as a stable concept. It was a shifting crust of molten silicates, constantly cracking open, reforming, and swallowing itself again. Imagine a world made entirely of fresh pizza cheese, stretchy, bubbling and impossible to walk on without disappearing into the goo. The chaos wasn't random, though. It was organized destruction. Every volcanic eruption released gases that thickened the early atmosphere, and every meteor strike stirred the cauldron further. Earth's infancy was a billion-year demolition derby where the rules were simple. Crash, burn, repeat. The energy released was so extreme that even the notion of day or night barely mattered. Everything glowed. The surface radiated a heat so intense it probably made the sun jealous. The sky looked nothing like it does now. It wasn't blue, it wasn't even gray. It was thick with ash, vapor, and metal dust, a murky, reddish haze that turned sunlight into a dim orange smear. Lightning flashed constantly, triggered by the immense heat differences in the atmosphere. You would have seen bolts of electricity ripping through volcanic clouds every few seconds, striking into oceans of magma and splitting gases apart into new chemical combinations. If Earth had an aesthetic at this time, it was apocalyptic rave. Meanwhile, gravity was doing its best to hold this chaos together. Every eruption and impact sent debris flying, but most of it fell back, pulled by the planet's growing mass. This constant recycling of molten material helped mix Earth's interior like a planetary blender. Heavy elements sank deeper, lighter ones floated upward, and the entire sphere turned into a dynamic, swirling machine of metal and rock. Even in this hellscape, the blueprint of a layered world was quietly taking shape, though no one would call it quiet. The temperature across the planet was high enough to keep metals in liquid form. Iron, nickel, and magnesium flowed like rivers beneath a thin, unstable crust. The upper layer cracked like burnt pudding skin, exposing glowing magma below. You could watch a mountain form and melt within the same afternoon, assuming you somehow survived the atmosphere long enough to watch anything at all. And then there were the meteors, constant, relentless, some the size of cities, others no bigger than houses, but all carrying the same message. Space is a rough neighborhood. Each impact vaporized huge portions of the surface, launching molten rock into orbit before it rained back down in fiery shards. Some scientists estimate that during this period, the energy released by these impacts equaled that of multiple atomic bombs every single second. Basically, the planet was being pummeled into shape. Oddly enough, this violence was essential. Without it, Earth would have remained a cold, inert ball of rock. The collisions stirred its interior, generating heat that kept the core molten and active. That molten core would one day power magnetic fields, shield the planet from radiation, and let it hold an atmosphere instead of losing it to space. So, while it looked like destruction, it was actually construction, just the universe's messiest version of it. Volcanic activity, too, played its role. Every eruption belched gases into the sky, creating the first rough outline of an atmosphere. It wasn't breathable, unless you were a fan of acid vapor and death, but it was a start. That thick blanket of gases trapped heat, slowing down, cooling, and protecting the surface from total freeze-out. In a weird way, volcanoes were both villains and heroes. Terrible to live with, vital for survival. Over time, though time was still an abstract concept in a world without clocks, the chaos began to develop rhythm. Magma currents shifted, solidifying in brief moments before melting again. The atmosphere thickened. Impacts grew slightly less frequent. But don't imagine peace. Imagine a storm that has learned to breathe between lightning strikes. That was progress. If you looked down from orbit, assuming you weren't vaporized by debris, you'd see a glowing, restless world, more star than planet. Streams of magma traced bright scars across its surface. Vast plumes of volcanic gas rose into the haze like ghostly pillars. The horizon shimmered with heat, and the ground was in constant motion, a liquid landscape reshaping itself every few minutes. It was terrifyingly alive. There's a strange poetry to this stage of Earth's life. Before there were oceans, there were lava seas. Before there were mountains, there were molten waves frozen mid-crash. Before there was life, there was movement. A planet learning how to change. The violence wasn't random. It was rehearsal. The chemistry of the atmosphere, the layering of the crust, the circulation of heat through the mantle, all of it was setting the stage for the calmer, cooler world to come. But that calm was still far away. For now, chaos ruled supreme and Earth was its crown jewel of disorder. The planet spun rapidly, its molten heart pumping energy outward, while the sky crackled with fury. This wasn't just the dawn of a world, it was a tantrum that built a home. From this furious beginning would rise oceans, continents, and life itself. But for now, it was just fire, gas, and gravity arguing loudly about who would get to shape the future. And in that argument, something remarkable was happening. A balance between destruction and creation. Every explosion wrote a line of the planet's first unwritten story. Every impact forged the ingredients that would one day make seas, air, and maybe even curiosity itself. The king of chaos wasn't just ruling. It was creating a kingdom. Let's rewind even further. Before the chaos, before the lava oceans, before the Earth even existed as a single thing. Picture a vast cosmic construction site about 4.5 billion years ago. The sun had just finished its dramatic entrance, igniting in a burst of nuclear fusion and clearing away a good deal of gas and dust from the solar nursery. But not everything got swept up into the solar spotlight. All around it swirled leftovers, bits of rock, ice, and metal that didn't quite make the cut. Think of it as the solar system's messy after-party. This leftover material wasn't peaceful. The early solar system was a violent demolition derby on an unimaginable scale. Every grain of dust was on a collision course with another, and every collision glued them together. At first, these were tiny clumps, particles no bigger than sand grains, sticking together through static electricity. You know that feeling when a sock clings to your shirt fresh out of the dryer? Now imagine that happening in space. But instead of laundry, it's dust and metal forming planets. These small clumps grew into pebbles, then into boulders, then into massive hunks called planetesimals. Each planetesimal was like a mini-world with its own gravity, which meant it could pull in more material. The process snowballed, literally, except instead of rolling downhill, these growing bodies tumbled through the vacuum, slamming into one another at speeds that would make any highway patrol officer faint. The impacts released enormous amounts of heat, melting rock and metal into glowing liquid droplets that emerged into larger and larger bodies. Earth began as one of these bodies, a cosmic collector of debris, gathering space crumbs with unrelenting greed. Every collision added mass and energy, and with that energy came heat. The more Earth grew, the hotter it became. It wasn't just from impacts, though. Radioactive elements inside the growing rock pile, uranium, thorium, and potassium, were quietly decaying, releasing heat like tiny nuclear reactors buried deep in the rubble. The result was a glowing, molten embryo of a planet, constantly stirred by cosmic collisions. Meanwhile, the solar system was still a wild place. The sun's gravity ruled the show, but Jupiter, massive and mischievous, played gravitational ping-pong with everything nearby. Asteroids and planetesimals were flung inward or outward, creating constant chaos. Some of that debris smashed into Earth, feeding its growth, while other bits were ejected into deep space, never to return. You could say Jupiter was the neighborhood bully, hurling rocks at the smaller kids. As the Earth grew, it began to differentiate, not in personality, but in structure. The heavier elements, melted by all that heat, started to sink inward. The lighter ones floated upward. But at this early buffet stage, everything was still mixing violently. Imagine a pot of soup boiling so vigorously that no ingredient stays still for more than a few seconds. Metals, silicates, ices, and gases were constantly churned, reshuffled, and occasionally vaporized. Somewhere around this time, the sun unleashed powerful solar winds, streams of charged particles that blasted through the inner solar system, sweeping away much of the lighter gases like hydrogen and helium. That's why Earth didn't end up as a gas giant like Jupiter or Saturn. We kept the heavier stuff: iron, silicon, carbon, and oxygen, while the fluffier materials were kicked out of town. It's as if the solar wind took one look at Earth's early ingredient list and said, "You're keeping the solids. No soup for you." The collisions that built Earth weren't just frequent, they were apocalyptic. Some of them hit with such force that entire sections of the young planet were vaporized. Molten rock splashed into orbit, some of which rained back down, adding even more heat. This was not a gentle birth. It was a cosmic fistfight where the prize was existence. But out of this cosmic chaos came something remarkable: order. As debris settled, Earth's orbit around the sun became more stable. The constant pelting slowed, though slowed is relative, since it still meant occasional city-sized asteroids dropping in uninvited. Gradually, the planet's shape smoothed into a sphere, gravity pulling every bit of molten matter toward the center. From that point onward, Earth was no longer just a random rock. It was a world in progress. Now, let's take a step back and appreciate how absurdly lucky this all was. The solar system was a crowded mess of potential planets, many of which didn't make it. Some were swallowed by the sun. Others collided and shattered into fragments, becoming the asteroid belt. But Earth managed to form at just the right distance, not too close to fry, not too far to freeze. Right in the so-called Goldilocks zone, where conditions were just right. Though just right at the time still meant temperatures hot enough to melt steel. Even then, the young planet wasn't done eating. It kept accreting material for hundreds of millions of years, sometimes gently, sometimes catastrophically. Each new impact reshaped its surface, adding layers and complexity. You could say Earth was binging on the universe's leftovers, building itself one crash at a time. The leftovers buffet didn't just shape Earth, it flavored it. The ingredients gathered during this period set the stage for everything to come. The iron and nickel that sank to the core would one day power magnetic fields. The silicates that floated upward would form crust. The trace elements, carbon, nitrogen, sulfur, would eventually seed chemistry vital for life. Every splattered rock, every molten merger, every radioactive decay was part of the recipe. And here's the cosmic irony. Out of the sun's leftovers came a planet capable of wondering about its own origins. Earth was assembled from debris, scraps, fragments, stardust, but those scraps had a destiny. The same chaos that built it also gave it character. It didn't need perfection to exist. It needed collisions, noise, and heat. The very things that look like destruction from afar were, in truth, creation in disguise. So the next time you hear someone call something space junk, remember you are literally made from it. Every atom in your body once drifted in that ancient debris cloud, waiting for gravity to pull it into place. The earth, the rocks beneath your feet, the iron in your blood, all leftovers from a stellar feast. In the greatest recycling project the universe ever ran, the scraps became a home, and the chaos became a planet that would one day look up at the stars and realize it was made of them. After the chaos of Earth's formation, there came a brief in geological terms, moment of stillness. Not peace exactly, but a pause in the relentless bombardment. The collisions that had once kept the planet churning were slowing, and the newborn Earth finally had a chance to take a breath. Except that breath smelled like hot metal, sulfur gas, and regret. The surface was still molten, but something new was happening deep within. The planet was starting to organize itself. The reason? Gravity, that quiet sculptor of the cosmos. Once Earth reached a certain size, gravity began pulling the denser materials, like iron and nickel, toward the center. This wasn't a graceful descent. Imagine billions of tons of molten metal sinking through rock like glowing raindrops falling through honey. Each drop released more heat, melting even more of the planet from the inside out. It was like setting the world's oven to broil and forgetting to turn it off for a few million years. This monumental reshuffling is what scientists call planetary differentiation. It sounds fancy, but it's really just the universe sorting its closet. Heavy metals went to the bottom. Lighter silicates rose toward the top, and gases tried to escape altogether. It was the first great act of order out of chaos, a planetary self-organization that would define Earth's inner structure for the rest of time. The planet was literally finding its center. At the heart of this process, the iron catastrophe, yes, it's called that, and yes, it earned the name, was underway. As molten iron sank inward, it dragged heat with it. The immense friction and compression generated enough energy to keep the entire planet molten even longer. The core became a blazing heart of metal, while the upper layers gradually cooled into something resembling solid rock. You could think of Earth as baking from the inside out, with the oven door permanently locked. The sinking of iron didn't just shape the planet's layers. It gave Earth one of its most defining features, its magnetic field. As the iron-rich core formed, it started spinning separately from the outer layers. That motion, combined with convection currents in the liquid outer core, generated a dynamo effect, a self-sustaining magnetic field. At this point in the planet's history, it wasn't yet strong enough to protect anything, because, well, there was nothing alive to protect. But the groundwork was set for one of Earth's future superpowers. Without that field, our atmosphere would have been stripped away by the sun's radiation long before life could have even been imagined. Meanwhile, above this newly forming core, lighter materials were rising and separating into layers of their own. The mantle, made mostly of silicate minerals, became the thick, viscous middle zone, churning slowly over millions of years. Above that, the crust began to crystallize, thin and fragile, like a film forming over cooling lava. It cracked easily, moved restlessly, and constantly recycled itself into the molten depths below. The crust was Earth's first attempt at solid ground, though at this stage standing on it would have been like standing on a hot pancake that occasionally flips itself over. The beauty of this process is that it turned random chaos into structure. For the first time, Earth wasn't just a blob of molten metal and rock. It had identity. The dense metallic core at the center, the flowing mantle above it, and the rocky crust on top made Earth a layered world, capable of holding heat, generating magnetism, and sustaining geological activity for billions of years. Every volcano, every earthquake, every mountain that would ever rise owes its existence to this ancient game of cosmic density sorting. And yet, this separation was anything but gentle. Imagine the sound, if sound could travel through molten rock, of an entire planet's worth of metal crashing inward. The process unleashed energy equivalent to countless atomic detonations happening all at once, deep below the surface. If there were any solid structures, they melted. If there were any early minerals forming, they vaporized. The heat radiating outward kept the outer layers molten for millions of years, ensuring that Earth remained a glowing cauldron long after its birth. Interestingly, this internal rearrangement also marked the first time the planet started acting like a living thing. Heat moved through its layers in convection currents like blood circulating through veins. The mantle churned slowly, hot material rising while cooler material sank. It was this internal motion that would later drive the shifting of continents and the eruption of volcanoes. Earth had become a restless organism of stone and fire, its heartbeat powered by gravity and radioactive decay. Above the molten mantle, the crust that began forming wasn't uniform. In some regions, lighter minerals like feldspar and quartz created thicker patches, while in others, denser basaltic material dominated. These early differences would eventually become the seeds of continents and ocean floors, but for now, the planet's surface was a chaotic patchwork of cooling rock, constantly broken and remade by volcanic fury. You could call it the first version of tectonics, the world's slowest game of lava whack-a-mole. As the crust thickened, gases trapped inside the planet began to find escape routes. volcanic eruptions spewed out carbon dioxide, nitrogen, and water vapor, ingredients that would one day form the atmosphere and oceans. But that comes later. At this stage, these gases did something else. They helped insulate the planet, trapping heat and keeping the internal cauldron simmering. In a strange way, the more Earth tried to cool down, the more its own behavior kept it hot. If you could stand outside the planet and watch it through time-lapse, say, over a few 100 million years, you'd see a mesmerizing transformation, a molten sphere gradually developing layers, like an onion made of fire and metal. You'd see glowing streams of iron sinking inward, swirling and merging at the core. You'd see lighter materials bubbling up, spreading thin sheets of rock that cracked and healed like skin. It was violent and magnificent, planetary metamorphosis in its purest form. And that transformation never really stopped. The separation of materials set off a chain reaction that continues to this day. The heat trapped inside keeps the mantle flowing, the core spinning, and the crust shifting. The same process that sorted iron from rock 4.5 billion years ago still powers volcanoes, earthquakes, and the slow dance of continents. Earth learned how to move from the inside out, and it's never forgotten the choreography. So, yes, iron made a heavy move, but it wasn't just gravity at play. It was destiny in motion. Without that great inward migration, the planet would be cold, lifeless, and magnetically mute. Instead, it became a world with structure, heat, and a pulse. The universe, in all its fiery indifference, had just invented layering. And in the furnace of that organization, Earth took one step closer to becoming a place where order could one day give rise to something extraordinary. Life. Take a deep breath. Now imagine doing that 4 billion years ago, and immediately regretting it. You wouldn't get air. You'd get a cocktail of gases that could melt your lungs faster than you could say, respiratory failure. Early Earth's sky was not blue, nor clear, nor remotely friendly. It was a murky veil of poison, a hazy dome swirling with volcanic gases and cosmic leftovers. This was not an atmosphere that welcomed life. It was an atmosphere that dared it to even try. Back then, the planet's surface was still cooling, but the inside of Earth remained a furnace. Volcanoes were everywhere, popping off like fireworks on fast forward. Each eruption blasted huge plumes of gas into the sky. Water vapor, carbon dioxide, methane, sulfur dioxide, ammonia. If you had been there, which thankfully you weren't, you'd have seen a world perpetually cloaked in thick, reddish-gray haze. The horizon was probably indistinguishable from the sky. Both were tinted with the burnt orange glow of sunlight filtering through toxic fumes. And that smell, good grief, that smell. The air was thick with hydrogen sulfide, the same gas that makes rotten eggs smell, well, rotten. Multiply that by 1 billion. Add in a splash of acid rain, and you've got the scent of the early Earth. It was the kind of air that would corrode metal, burn skin, and turn clouds into potential fire hazards. Scientists call it a reducing atmosphere, meaning it lacked oxygen and was dominated by gases that prefer to gain electrons rather than lose them. But in simpler terms, it was the kind of place where even metal would hesitate to rust. because rusting requires oxygen, and oxygen hadn't even been invented yet. So where did this poisonous soup come from? It was Earth burping itself into existence. The gases that filled the early atmosphere were trapped inside the planet during formation, locked away in minerals and molten rock. As the surface cooled and solidified, volcanic outgassing released them in vast quantities. Think of Earth as a teenager hitting its rebellious phase. Unpredictable eruptions, bad temper, constant outbursts. The air above reflected that personality perfectly. Chaotic, unstable, and downright moody. The sun's light had little luck penetrating this dense smog. Daytime on early Earth was more of a dim orange twilight, the sun a blurry disk rather than a bright star. And because there was no ozone layer yet, ultraviolet radiation streamed down unchecked. The irony was painful. Too much atmosphere to see through, but not enough protection to survive under. The surface roasted beneath a greenhouse effect so intense that it trapped heat like an oven door sealed shut. The thick blanket of carbon dioxide and methane made sure that once heat came in, it wasn't going anywhere. Rain, when it happened, wasn't the refreshing kind either. Water vapor from volcanic eruptions condensed in the upper atmosphere, mixed with sulfur dioxide, and came back down as acid rain strong enough to etch stone. Imagine standing in a storm where every raindrop is basically vinegar's angry cousin. The landscape was constantly washed in this chemical rain, dissolving minerals, changing rocks, and feeding the first primitive reactions that would one day set the stage for life. Lightning was another frequent visitor. The early atmosphere, packed with volcanic ash and charged particles, was a perfect playground for electrical storms. Bolts of lightning streaked across the toxic sky, igniting chemical reactions in the gases below. Every strike shattered molecules, reshuffling atoms into new compounds. Hydrogen cyanide, formaldehyde, and other exotic molecules that would one day become important ingredients in the recipe for life. In a strange twist, the same deadly air that could suffocate you was also cooking up the molecules that would make breathing possible billions of years later. But at this stage, life-friendly was still a cosmic joke. The air pressure may have been higher than today's, with a greenhouse effect that made the planet stifling hot. The seas, if they existed, boiled near volcanic vents, absorbing gases from the sky and turning them into strange chemical stews. The sky and sea traded poisons like gossip, carbon dioxide dissolving into water, sulfur compounds drifting upward, ammonia being broken down by sunlight into nitrogen and hydrogen. It was an endless atmospheric chemistry lab, the ultimate natural experiment where explosions were part of the curriculum. And through it all, the sky would have been beautiful in a horrifying way. No stars visible through the haze, but perhaps an eerie red glow stretching from horizon to horizon, illuminated by the flicker of distant eruptions. You might have seen streaks of lightning tracing across dense clouds, flashes of purple and white that briefly revealed the shadowy outline of a restless world below. If you had to describe it, you'd say it looked like Mars and Venus had a chaotic child, and they raised it on fire and brimstone. It's tempting to think of this atmosphere as purely destructive, but it was also creative in its own twisted way. Without oxygen, fragile molecules could form and persist without being immediately destroyed. Gases like methane and ammonia interacted with sunlight, creating organic compounds that rained down into the early oceans. The very air that would have killed you was, paradoxically, building the ingredients that could one day make you possible. It was the universe's version of tough love. Meanwhile, the lack of oxygen meant there was no protective ozone layer, leaving the planet's surface constantly bombarded by ultraviolet radiation. But this radiation wasn't all bad news. It also drove energy into chemical bonds, jump-starting reactions that might otherwise never have happened. Earth's poisonous sky was, in essence, a massive photochemical factory. Every molecule of gas, every flash of lightning, every droplet of acid rain was part of a global experiment in transformation. As the centuries turned to eons, the thick air began to evolve. Volcanoes still belched, but their outputs changed slightly as the crust matured. The balance of gases shifted, and the atmosphere gradually grew thinner. But oxygen was still nowhere to be found. For now, the sky belonged to poisons, to methane and ammonia, to sulfur and carbon dioxide. It was a hostile, alien world, one where breathing would be fatal and the sunsets would look like the end of time. Yet within that fiery veil, the chemistry of life was brewing quietly, unseen. The air was toxic, the water corrosive, the light harsh, but it was a beginning. A dangerous, ugly, magnificent beginning. The atmosphere didn't just hang over the earth, it sculpted it. It carved rivers of acid, reshaped minerals, and altered the planet's chemistry at every level. It was both destroyer and creator, both the planet's curse and its preparation. The sky was full of poison, yes, but that poison was destiny in disguise, the raw material from which a breathable world would one day emerge. It began, as all cosmic dramas do, with a collision that defied reason. Earth was still young, still a molten wanderer in the crowded solar neighborhood, when it met Theia, a protoplanet roughly the size of Mars. Theia wasn't an invader, exactly. It had been orbiting the Sun in roughly the same lane as Earth, probably for millions of years. But orbital mechanics can be cruel, and small gravitational nudges from other planets gradually set the two on a catastrophic rendezvous. The result wasn't a polite bump. It was the single most consequential smash-up in our planet's history. The impact happened fast. At a closing speed of nearly 15 kilometers per second, Theia hit Earth at an angle. Scientists estimate around 45 degrees, transforming both worlds in an instant. The force released was beyond comprehension. If you tried to measure it, you'd get numbers that make supernovae seem like gentle sighs. In less than a heartbeat, Earth's crust and mantle vaporized near the point of impact. Oceans of magma were hurled skyward. Mountains of rock turned into vapor and plasma. Theia itself didn't survive. The planet that struck us ceased to exist as a distinct body, its remains merging with Earth and scattering into space. For a brief moment, Earth became unrecognizable. The entire planet liquefied again, erasing whatever fragile crust had started to form. The atmosphere was stripped away and replaced by cloudeds of molten rock vapor. The surface glowed white-hot, radiating energy into space like a second sun. This was no mere planetary scar. It was a complete reset. Earth had been destroyed and reborn in the same breath. But in destruction there was creation. a vast plume of debris shot into orbit around the planet. Trillions of tons of molten rock, silicate vapor, and shattered thean remains. These fragments spread out into a disk, encircling the Earth like a fiery halo. From afar, it might have looked almost peaceful, a glowing ring of molten rubble floating above a molten planet. In reality, every chunk was colliding, merging, and shattering again in a violent ballet of gravitational chaos. Over time, perhaps just a few thousand years, a blink in cosmic time, the chaos began to settle. The molten debris gradually coalesced, clumping together into a single massive body. As it orbited, it pulled itself into a sphere. That body became the moon, a child born from fire and fury. It was not captured, not adopted from elsewhere. It was born of the earth itself, forged from our planet's own flesh. When the moon first formed, it was far closer to Earth than it is today, so close that it would have loomed gigantic in the sky, hundreds of times larger than what we see now. Its gravitational pull raised tides not of water, but of molten rock. Imagine lava oceans sloshing back and forth in rhythm, with a baby moon hanging low and massive in a sky filled with vaporized stone. It was beautiful in a deeply unsettling way, like watching creation itself caught mid-explosion. This impact didn't just give Earth a companion, it changed everything about how our planet behaves. Before the collision, Earth likely spun much faster, perhaps completing a full rotation in just a few hours. The impact transferred angular momentum, slowing Earth's spin and tilting its axis. That tilt, about 23 degrees, would become crucial much later for creating seasons. The moon's gravitational tug has kept that tilt relatively stable ever since. Without it, Earth's axis might wobble wildly over time, turning climate into a chaotic mess where the poles could trade places with the tropics. In other words, that ancient cosmic punch didn't just make the moon, it made stability possible. But the story doesn't end with the moon's creation. The Earth and its newborn satellite began a complex gravitational dance that continues even now. In the beginning, the moon orbited just 25,000 kilometers away, so close that it whipped around the planet every few hours. Over billions of years, tidal interactions between the two have gradually pushed the moon farther out. Even today, it's still drifting away from us, inch by inch, like a roommate slowly packing up and moving to the suburbs. Meanwhile, the heat from the collision lingered for a long time. The outer layer of Earth remained molten for millions of years after the impact, its crust a glowing skin that hardened and cracked as it cooled. The new moon wasn't much better off. It too began as a molten body, with volcanic plains and a magma ocean of its own. Slowly, both worlds began to solidify, their fiery tempers cooling into the rocky faces we recognize today. The scars of that collision are still written across them. Earth's iron-rich core may have swallowed Thea's metallic heart, and the moon's composition matches Earth's outer layers almost perfectly, as if they were once part of the same body, because they were. What's truly poetic about this cosmic catastrophe is how much balance it brought. The moon's gravity tugs at Earth's oceans, creating tides that would one day shape coastal ecosystems and influence the rhythms of life. Its steadying presence ensures our planet's climate remains relatively predictable, allowing life to adapt and flourish over geological time. Even our days, 24 hours long, owe their length to that collision. Without Thea's grand entrance, Earth might still spin so fast that a day would last just 6 hours. Imagine trying to get enough sleep in that world. The impact also flung away much of the volatile material that might have made Earth more like Venus, a dense, choking atmosphere of carbon dioxide. In a strange way, Thea's destruction helped prevent our planet from becoming a permanent furnace. The collision purified Earth, giving it a fresh start. Lighter, leaner, more stable, and in the long run, more hospitable. Of course, at the time it didn't look hospitable at all. The sky glowed with molten debris, and each night the moon would have hung enormous and red, slowly cooling as it orbited above the still scorched planet. It was a scene of destruction so complete it bordered on divine. Creation through devastation, order born of chaos. And so the moon came to be, not from a calm or chance, but from violence. A planetary collision that should have been an ending instead became a beginning. Earth was scarred, reshaped, and forever altered, but it gained a companion that would watch over it for billions of years to come. Every tide, every eclipse, every pale glow that lights up our nights is a reminder of that ancient impact when one world struck another, and from their union a new one was born. Imagine standing on the newly solidifying Earth, if standing were possible, without immediately melting your shoes and everything else you own. The once molten surface had begun to harden, cracking and cooling after eons of cosmic punishment. The atmosphere above was still a cocktail of poison, but it had something new in abundance: water vapor. Volcanic eruptions had been belching steam for millions of years, and as the planet's surface temperature dropped just enough that steam began to condense. And when it did, the skies opened. It didn't rain for a day, or a week, or even a century. It rained for thousands, possibly millions of years. Imagine a downpour so relentless that the horizon blurred into a gray curtain of water. Lightning flashing through clouds so thick they never cleared. Raindrops the size of bullets hissed against still warm rock, instantly turning into plumes of vapor. Rivers didn't yet exist, so the water spread out in sheets, rushing into cracks, filling impact craters, and carving the first shallow basins. The surface of Earth became a battlefield between fire and flood. Lava met rain, stone hissed and cracked, and steam rose in endless towers that darkened the sky. The planet's crust was finally beginning to cool in earnest. Every drop of rain that struck it drew away a tiny fraction of its heat. Over time, the relentless deluge began to win. The uppermost layers solidified further, thickening into a crust capable of holding water. Pools became ponds, ponds merged into lakes, and those lakes spilled together to form the first true oceans. It was as if the planet itself sighed, a long, steaming exhale after an eternity of rage. But where did all that water come from in the first place? The answer is everywhere. A portion of it came from deep within Earth. Water molecules trapped inside minerals during the planet's formation were released through volcanic eruptions, bubbling up as steam. You could say the planet was sweating out its insides. The other portion came from space. During the tail end of Earth's formation, icy comets and water-rich asteroids slammed into the planet by the millions, delivering frozen cargo from the outer solar system. Each impact released more vapor, adding to the growing atmospheric stew. In cosmic terms, it was as if the universe had ordered a water delivery, though the shipping method was, let's say, aggressive. As the rain continued, the transformation was dramatic. The once fiery surface darkened, first from cooling basalt, then from the forming pools of liquid water. The air was still toxic, rich in carbon dioxide, methane, and sulfur, but it began to thicken with clouds, regulating heat in new ways. Beneath the heavy sky, the young oceans began absorbing gases from the air, dissolving carbon dioxide and sulfur compounds, slowly altering the planet's chemistry. The cycle of water, evaporation, condensation, precipitation had begun, though in these early days it was more like evaporation, apocalypse, and repeat. If you could somehow fly above this newborn Earth, it would have been an astonishing sight. Vast stretches of black rock glistened with torrents of rain. Rivers of runoff streaked between glowing volcanic ridges, carving canyons through still cooling lava. Massive storms raged without pause, with thunder that rolled endlessly across the planet. Lightning struck so often that it may have lit up the entire sky, fueling chemical reactions in the atmosphere and oceans. The air shimmered with ionized gas, while below, sheets of water met magma in clouds of steam that rose like living mountains. Over time, gravity gathered the water into the planet's lowest regions, those primordial basins formed by ancient impacts and tectonic sagging. The first proto-oceans took shape, filling with rainwater, melted comet ice, and dissolved minerals. They were nothing like the clear blue seas we know today. These waters were dark, acidic, and thick with dissolved metals. Iron gave them a rusty hue, while sulfur compounds turned them yellow-green in places. Picture a world of steaming pools, not unlike a planet-sized chemical lab, each wave whispering alchemy. The constant rain also had another important job. It scrubbed the atmosphere. As water vapor condensed and fell, it dragged particles and gases with it, carbon dioxide, sulfur dioxide, and dust. The atmosphere slowly lost some of its density, clearing just enough for light to filter through. For the first time, sunlight began to reach the surface consistently, glinting off vast, rippling oceans. The sun's reflection danced across waters that, though still poisonous, signaled the beginning of Earth's transformation into a more temperate world. And those oceans didn't just cool the planet, they shaped it. The enormous weight of the accumulating water pressed down on the crust, causing it to sag in places and rise in others. This flexing and shifting laid the groundwork for future plate movement. The interaction between water and rock began to weather the surface, breaking down minerals and carrying their dissolved contents into the seas. These reactions created a rich chemical soup, the kind of brew that would later become the cradle for life's earliest experiments. The Earth was effectively stirring its own cauldron of possibilities. The world at this stage was quieter than before, but only by comparison. Volcanoes still rumbled, spewing ash and steam into the sky, replenishing what the rain pulled down. Each eruption added more gases to the atmosphere and more minerals to the oceans. The balance between these forces, volcanic fury and watery persistence, became Earth's new rhythm. Fire would never truly vanish. It simply learned to coexist with water. As the planet continued to cool, the rains began to ease. The atmosphere stabilized into thick clouds and intermittent storms. The first oceans, now vast and stable, covered much of the planet's surface, shimmering beneath the dim orange sunlight that still struggled through the haze. The air remained poisonous to us, but to the planet it was nourishment. Water vapor, carbon dioxide, and heat worked together to keep the surface from freezing, maintaining a fragile equilibrium. If you could stand on the shore of that early ocean, you'd witness something both alien and oddly peaceful. The waves would hiss and steam as they touched still warm rocks. The horizon would fade into a thick amber fog. Above, the moon, still enormous and close, would loom like a glowing guardian, pulling at the tides of these infant seas. It was a world remade. From molten fire to endless rain, from chaos to rhythm. The oceans were more than water. They were memory. Every drop carried traces of comets, volcanoes, and cosmic dust. Together they formed a mirror, reflecting a calmer planet and marking the start of something entirely new. For the first time, Earth could cool, reflect sunlight, and sustain chemistry long enough for complexity to emerge. The storm had finally become a sanctuary. So, when oceans fell from the sky, they didn't just quench the planet's heat, they baptized it. In that endless rain, Earth washed away the last traces of its fiery youth, trading chaos for balance and fire for reflection. And in those dark, restless seas, something extraordinary was about to stir. At long last, after eons of violent collisions, relentless rain, and seething magma, Earth began to cool enough to start forming something solid. It wasn't a sudden change. It was more like a slow exhale after an eternity of holding its breath. The fiery skin of the planet finally started to harden, and the molten world that once glowed like a forge began to grow a crust, a fragile, wrinkled shell over its restless interior. For the first time, Earth had skin instead of scars. This crust wasn't the steady continental stuff we walk on today. It was thin, brittle, and constantly breaking under pressure. The early crust formed, melted, and reformed repeatedly, caught in a loop of creation and destruction. Imagine baking a cake that keeps collapsing in the oven and trying to frost it anyway. That was Earth's early geology. The planet was still losing heat rapidly from its molten core, and that heat escaped through thousands of volcanic vents, keeping the crust alive with motion. But eventually, amid the turmoil, tiny, solid fragments managed to endure. Among these survivors were zircons, minute crystals that could fit on the tip of a needle yet hold secrets older than any mountain or ocean. Zircon minerals are remarkable because they can withstand immense heat and pressure without losing their internal chemical record. They are nature's archivists, storing information about temperature, pressure, and even the presence of water from the time they formed. The oldest known zircon crystals, discovered in Western Australia's Jack Hills, are about 4.4 billion years old. To put that in perspective, if Earth's history were a 4-hour day, those zircons appeared just 10 minutes after midnight, when the world had barely finished forming. They are, quite literally, Earth's baby teeth, the first minerals to survive the planet's violent childhood. What these zircons tell us is astonishing. Chemical traces within them, specifically the ratios of oxygen isotopes, suggest that liquid water already existed when they formed. That means that even amid the chaos, Earth had cooled enough for oceans to stabilize, and possibly even for rain to erode early rock. The image of a hellish, molten planet begins to soften. Beneath the steam and clouds, there were rocky surfaces being shaped by water's persistent touch. But the crust of that era wasn't all one piece. It was a fractured mosaic, constantly reshaped by the restless mantle below. The early crust probably resembled a network of volcanic islands and lava plains rather than large continents. Magma oozed through cracks. New rock solidified on top of old, and then the whole mess melted again. It was geology's equivalent of trial and error. Some sections sank back into the mantle under their own weight, while others managed to float, light enough to survive the infernal churn below. The type of crust that first formed was primarily basaltic, rich in iron and magnesium. It was dark, dense, and volcanic, a far cry from the lighter continental crust that would come later. These early rocks were forged from magma that cooled quickly at the surface, producing fine-grained, dense formations that paved the first stable patches of land. Each eruption added new material, layering the planet in dark stone until, at last, there was something you could, theoretically, stand on. If you didn't mind standing on 800-degree rock surrounded by a toxic sky, that is. As the crust thickened, the relationship between Earth's surface and its interior began to change. Heat from the mantle no longer escaped as easily, so the crust acted like a lid on a simmering pot. Pressure built up beneath it, and when that pressure was released, entire regions cracked open. Volcanic activity during this period wasn't localized. It was global. Rivers of lava stretched across hundreds of kilometers, and eruptions would have made modern volcanoes look like birthday candles. But despite the fury, something miraculous was happening. The crust was learning endurance. Slowly, mineral diversity began to increase. Cooling magma formed new types of crystals: feldspar, quartz, olivine. These minerals combined and recombined under extreme conditions, creating complex rocks like granite. Granite was crucial because it was lighter than basalt and could float on top of denser material, forming the nuclei of future continents. You could think of these early granitic formations as the planet's first attempt at landmass. Proto-continents rising like bubbles through a thick stew of molten rock. And, with the appearance of these rocks, came the planet's first geological memory. The minerals preserved chemical fingerprints of their origins. How hot it was, how much pressure they endured, what kind of atmosphere surrounded them. These tiny structures became storytellers, whispering across billions of years about a time when the world was still half fire, half dream. Even as the crust strengthened, the dance between creation and destruction never stopped. Earth was already experimenting with processes that would one day become plate tectonics. Sections of crust shifted, collided, and sank beneath one another, dragged down into the mantle where they melted and re-emerged. The surface was dynamic, a living skin that healed itself through fire. Every rock carried the memory of its death and rebirth, an eternal cycle that would shape the planet's future landscapes. Meanwhile, water continued to play its quiet role, seeping into cracks, cooling lava, and beginning the long process of erosion. As rain fell on the freshly formed crust, it interacted with minerals to create new chemical environments. Weathering released elements like sodium, calcium, and silicon into the oceans, subtly changing their chemistry. The balance between rock, air, and water began to stabilize. For the first time, the planet was not just a sphere of molten fury. It was a functioning system. If you could have stood on those early rocks, an impossible feat, but let's imagine, you'd have seen a surreal world. Dark plains of cooling lava stretching to a misty horizon, steam rising from fissures, and the vast, boiling oceans shimmering nearby. The ground beneath your feet would still tremble, the air thick with volcanic haze, and the heat would shimmer around you like a mirage. Yet, in that uninhabitable landscape, Earth was finally becoming recognizable. A planet with a surface, with structure, and with a story written in stone. The birth of rocks and crust wasn't just the end of Earth's fiery chaos. It was the beginning of permanence. These early formations became the foundation upon which everything else would rest. The continents, the oceans, and eventually, life itself. Those tiny zircon crystals, quietly enduring through 4 billion years of transformation, are not just minerals. They are the first words of Earth's autobiography, the record of a planet learning how to exist. The crust didn't just cool, it remembered. And in that memory lay the blueprint for everything that would come after. By the time Earth had cooled enough to hold steady oceans and a hardened crust, something extraordinary began to happen, not in the sky or the mountains, but in the smallest, quietest corners of the planet. The chaos that had once been purely physical, the fire, the rain, the endless crashing, was now chemical. The surface of the Earth had become a planetary laboratory, and the ingredients were ready: water, minerals, heat, and time. The recipe was simple. The results would be everything. Those early oceans were nothing like the serene blue expanses we see today. They were dark, metallic, and thick with dissolved minerals and gases. Think of them less as tranquil beaches and more as planetary soup, one that simmered endlessly under a thick, toxic sky. Into this brew fell a steady drizzle of molecules from space. Carbon compounds, ammonia, and hydrogen cyanide delivered by comets, asteroids, and interplanetary dust. Each impact brought new ingredients to stir into the mix, adding flavors from across the solar system. Earth wasn't just a planet, it was a cosmic blender. Lightning was everywhere. The young atmosphere, filled with methane and ammonia, was an ideal conductor for massive electrical storms. Bolts ripped through the sky like strobe lights at the universe's most dangerous rave. Every strike unleashed enough energy to rip apart simple molecules and fuse them into new ones, chains of carbon, nitrogen, and hydrogen that began to resemble the building blocks of life. You could say nature was running its own version of chemistry class, where the final exam was invent self-replication. Meanwhile, deep beneath the oceans, volcanic activity created another type of chemical playground. At the ocean floor, hydrothermal vents spewed superheated water rich with metals and sulfur. These vents acted like natural reactors, pumping out minerals that could catalyze complex chemical reactions. The contrast between the scorching vent fluids and the cold surrounding seawater created gradients of energy, a perfect setting for molecules to organize, combine, and test out new forms. In these strange, dark places, Earth was quietly performing experiments no scientist could ever replicate perfectly today. On the ocean's surface, ultraviolet radiation from the sun poured through the still thin atmosphere, breaking apart molecules in a process called photolysis. It was brutal, indiscriminate, and essential. UV light didn't just destroy, it also rearranged. Molecules split apart and recombined into new structures, some fragile, some stable. Carbon dioxide and methane reacted under sunlight, forming organic haze and more complex hydrocarbons. The result was a global chemical workshop powered by sunlight and lightning, operating 24/7 with no safety regulations whatsoever. If you could travel back to witness it, you wouldn't see life yet, but you'd sense its potential everywhere. The seas shimmered with oil-like films of organic material, a scum of chemistry floating on the waves. The air smelled sharp and sulphurous, and the horizon was often lit by storms. The planet seemed alive with movement, even though it wasn't yet. What was happening beneath the surface was the slow, invisible shift from random reactions to organized systems. Molecules began forming chains and rings, testing their ability to stick together and persist in a turbulent world. Among the emerging cast of chemical characters were amino acids, fatty acids, and simple sugars, the precursors of proteins, membranes, and energy molecules. None of these things were alive, but they were starting to behave as if they wanted to be. Some formed droplets surrounded by thin membranes, little bubbles that could trap other chemicals inside. Others began linking up into chains, forming the first primitive polymers. These were the early whispers of structure, the raw materials of complexity forming spontaneously, given only energy and time. One of the strangest ideas in this period of Earth's history is how cooperative it all was. No single reaction created life. It was a chorus of them, overlapping and feeding off one another. The volcanic gases fed the lightning chemistry. The lightning-created molecules drifted into the ocean. The ocean reactions produced minerals that fed the vents. It was a feedback loop of creation, a world where even destruction contributed to possibility. Every flash of lightning, every bubble from a vent, every wave washing against a mineral shore nudged the chemistry forward a little more. On certain coastlines, where volcanic rock met the sea, minerals acted as catalysts, accelerating reactions that might have otherwise taken centuries. Clays, in particular, played a crucial role. Their layered structures could trap organic molecules between sheets, concentrating them and forcing them to interact. Imagine a mineral notebook. Its pages filled not with words, but with the planet's earliest chemical stories. Those clays might have been where molecules first learned to organize in patterns, to encode, to replicate, to evolve. This was the ultimate paradox. The same forces that had once made Earth uninhabitable were now giving it everything it needed to host life. Lightning, radiation, and volcanic heat, all forms of destruction, were now engines of creation. The harshness of the planet was not a flaw, it was the secret ingredient. It provided energy, diversity, and motion. Without that relentless instability, chemistry would have stagnated. Instead, it danced. As millions of years passed, the oceans became thick with organic material. Molecules floated, collided, broke apart, and reassembled endlessly, like a cosmic shuffle deck. Some arrangements were fleeting, others lingered longer, learning to persist. It was evolution before biology, competition before consciousness. The ingredients were there, but the instructions were still unwritten. Somewhere within this chemical carnival, a new pattern was emerging, one that could store information and make copies of itself. And though it would take eons more for that spark to catch, the stage was perfectly set. The planet had cooled enough to be stable, yet remained active enough to stir its oceans like a giant cauldron. The air was toxic to modern lungs, but perfect for building molecules that oxygen would destroy. The lightning flashed on cue, the vents bubbled constantly, and the sunlight provided just enough chaos to keep the chemistry interesting. It was in this restless, beautiful mess that nature began its greatest experiment. An experiment that didn't know its purpose, didn't have an audience, and didn't need one. The oceans were the beakers, the sky was the spark, and the planet itself was the lab bench. One day, those aimless molecules would cross the invisible line from chemistry to biology, and life would begin. But for now, Earth was content to keep mixing its primordial potion, bubbling, glowing, and endlessly changing. The planet wasn't alive yet, but it was dreaming about it. The oceans had become restless with potential. For millions of years, Earth's surface chemistry had been bubbling like an overexcited potion, throwing molecules together in every conceivable combination. Most of those combinations were meaningless, unstable, fleeting, or doomed to dissolve. But in a few extraordinary cases, something began to happen that would change everything. Molecules started behaving less like ingredients and more like instructions. To understand this transformation, you have to imagine the world as a vast experiment running on chaos and chance. The oceans were thick with amino acids, the building blocks of proteins, formed in countless ways. Sparked by lightning, synthesized near volcanic vents, or delivered by asteroids carrying organic compounds forged in distant stars. Floating among them were simple sugars and fatty acids, molecules that could clump together into thin films or spherical bubbles. These weren't cells yet, but they were trying their best to play the part. The early Earth was a planet of chemical near misses. Most reactions ended in failure, producing unstable goo that fell apart as quickly as it formed. But chemistry, given enough time, is persistent. The same reactions played out billions upon billions of times, every second, across oceans, lakes, and tidal pools. Somewhere in that endless repetition, patterns began to emerge. Molecules that could survive a little longer, link up a little tighter, or even influence what came next. It was trial and error on a planetary scale, and error was doing most of the work. Among the most promising characters in this pre-life drama were molecules capable of holding information. Today, DNA and RNA are the famous stars of that role, carrying the blueprints for every living thing. But back then, no such elegant system existed yet. Instead, there may have been simpler strands, short chains of nucleotides that accidentally formed in the right order, capable of copying themselves under the right conditions. These primitive polymers weren't alive, but they were the first things that acted like they wanted to be. This moment, when chemistry crossed the line into self-replication, is one of the most mysterious transitions in science. It's the point where stuff becomes something. No fossil records mark it. No single molecule declares, "I am alive now." But we know it happened, because everything that followed, cells, evolution, consciousness, depends on that leap. Life didn't start with a bang. It started with a whisper, a single chemical reaction that happened to make a copy of itself before fading away. And then it happened again, and again. And eventually, one of those self-replicating systems stumbled upon a trick: variation. Small changes in structure led to differences in stability. Some survived heat or radiation better than others. Those lucky molecules lingered longer, multiplied more effectively, and gradually took over their microscopic neighborhoods. Evolution had just entered the chat, but these molecules didn't float alone. They were surrounded by other structures, lipid bubbles that could trap them inside. These bubbles, made from fatty acids, formed naturally when such molecules touched water. They organized into double layers, creating tiny enclosures that could separate inside from outside. It was chemistry's version of building a fence, and it was revolutionary. Inside those fragile bubbles, reactions could proceed differently than in the open ocean. Molecules had their first private laboratory, a place to gather and refine without interference from the chaos outside. The combination of replicating molecules and enclosing membranes created something entirely new, a system that could grow, copy, and evolve. Still not alive, but very close. It's like the universe was slowly writing a recipe, and it had just figured out the part about combining wet ingredients with structure. All it needed now was persistence. The environment of early Earth gave that persistence in abundance. Thermal vents on the seafloor provided stable energy gradients, warmth, minerals, and chemical fuel that could power these reactions. Shallow tidal pools, alternately drying and refilling, concentrated molecules into dense films where interactions happened faster. Lightning storms provided bursts of energy to rearrange stubborn bonds. Even meteorite impacts, violent as they were, churned the chemistry and offered new starting materials. Every corner of the planet was a different flavor of experiment, running simultaneously for millions of years. In some places, these primitive chemical systems may have formed short-lived networks, molecules that supported one another's formation, like a team of molecules high-fiving across a puddle. Over time, cooperation replaced chaos. These networks became more resilient, developing feedback loops that allowed them to repair themselves and even adapt. The line between chemistry and biology blurred so thoroughly that even now, billions of years later, we still struggle to define exactly when one became the other. The earliest, almost life probably looked nothing like what we think of as living today. There were no cells, no DNA, no metabolism in the modern sense, just clusters of molecules, lipids, amino acids, and nucleotides, constantly assembling, breaking, and reforming. But some combinations lasted longer than others, and some developed the ability to harness energy from their surroundings. Perhaps a molecule learned to capture sunlight, or to tap into the chemical energy near a volcanic vent. Those that did gained an advantage, and the game changed once again. And then, at some point, perhaps in a tide pool or in the dark beneath the sea, a threshold was crossed. One of these primitive chemical systems achieved a true self-sufficiency. It could copy itself, use energy, and repair its structure. It could persist through cycles of destruction. That was it. The spark of life, quiet and unremarkable in the moment, had arrived. It's humbling to think that all the complexity of existence, plants, animals, languages, and space probes, began with a few lucky molecules drifting in the ocean, bumping into each other until something clicked. There was no plan, no direction, no supervising deity with a pipette and clipboard. Just atoms obeying physics and chemistry, discovering by pure accident that organization can emerge from chaos. No one invited life to the party, but once it showed up, it refused to leave. The oceans that once boiled with meaningless reactions now pulsed with purpose, and every molecule that managed to copy itself left a trace of that first defiance against disorder. From there, evolution would take over, sculpting these microscopic survivors into the architects of a living world. So began the quietest revolution in history, a rebellion not of fire or stone, but of molecules deciding to persist. Earth, once a stage of storms and magma, had just gained a new kind of storm, the storm of life, whispering through water, rewriting what it meant to exist. If someone could have looked at Earth during this era, from orbit, say, they might have mistaken it for a world still waiting to wake up. The surface was calm, almost eerily so. The violent bombardments had ended, the lava seas had cooled, and thick clouds drifted lazily over endless dark oceans. From space, it would have looked peaceful, almost dead. But beneath that stillness, under the weight of kilometers of seawater, the real story was beginning, so slowly, so quietly, that the universe itself might not have noticed. This was the Hadean's hangover and the dawn of the Archean, the time when life began its long, invisible rehearsal. The oceans, once chemical cauldrons, had settled into stable reservoirs of mineral-rich water. Hydrothermal vents hissed along the seafloor, exhaling clouds of hot, mineral-saturated fluid. Around those vents and in shallower seas, microscopic life, if we can even call it that yet, was stirring, not plants or animals, not even full-fledged cells as we know them, but fragile, experimental forms of existence. Molecules that copied themselves, learned to harness energy, and slowly evolved into true organisms. The planet, in these quiet ages, was a different kind of active. The roar of meteor impacts had been replaced by the hum of chemistry. Evolution, still half asleep, was testing out new blueprints, molecules that could store energy more efficiently, membranes that could better separate inside from outside, and primitive enzymes that could speed up reactions without burning out. Each microscopic success was fleeting. Replication without perfection, survival without certainty. But every little improvement left an echo for the next generation of molecules to inherit. The first true cells probably emerged in this era, simple single-celled organisms known as prokaryotes. They were tiny, unassuming, and astonishingly resilient. These pioneers didn't need sunlight or oxygen. They lived on chemical energy from the Earth itself. Some fed on hydrogen, sulfur, or iron, chemosynthetic microbes that turned geological processes into biological fuel. Imagine creatures so tough they could thrive in boiling water, acidic pools, or under crushing pressure. These early cells didn't just survive the world, they adapted to it, using every hostile condition as an opportunity. And yet, despite this microscopic flurry of activity, the world looked utterly barren. There were no forests, no coral reefs, no sound but the wind and the waves. The continents, if they existed at all, were small, rocky outcroppings surrounded by endless seas. The air was thick with carbon dioxide, giving the sky a hazy reddish tint. The sun's light was weaker than today's, and the days were shorter, as Earth still spun faster. It was a planet in slow motion, with life learning patience as its first evolutionary skill. The ocean floor became the stage for most of the action. Hydrothermal vents, in particular, were like tiny alien worlds within the larger planet. Black smoker chimneys spewed out minerals that built strange structures around them, columns of rock and metal, shimmering with heat and chemistry. Around these vents, primitive microbes clung to existence, forming thin films on rock surfaces. They fed on the chemicals erupting from the planet's interior: methane, hydrogen sulfide, and iron ions, and in doing so, they began the first ecosystems. There was no sunlight here, only chemistry. But chemistry, it turned out, was enough. Somewhere in those dark waters, another evolutionary leap was happening. Certain microbes began to figure out how to use sunlight, capturing its energy through a process that would one day become photosynthesis. But these earliest versions didn't produce oxygen yet. They used simpler molecules like hydrogen or sulfur compounds to extract energy. The oxygen revolution was still far off in the future. For now, life lived in secret, leaving almost no mark on the world above. If you could scoop up a handful of seawater from this time and look at it under a microscope, you might see tiny cells, spherical, rod-shaped, or spiral, drifting lazily, dividing slowly, oblivious to the fact that they were inventing biology. They would look simple, but their internal chemistry was remarkably sophisticated. Each one was a self-contained system, capable of storing information, consuming energy, and reproducing. It was life's first fully functional prototype, and it worked so well that the basic blueprint still exists today in the bacteria that populate every corner of our modern world. But for hundreds of millions of years, that was it. No multicellular life, no complex forms, just microscopic persistence. It was an age of refinement, not innovation. Evolution taking its time to fine-tune the machinery of living systems. Genetic material became more reliable, metabolic pathways more efficient, and membranes more robust. Evolution didn't rush because it couldn't. Every improvement took countless generations to appear, each one a tiny chemical nudge toward complexity. And while life quietly perfected itself beneath the waves, the planet above was slowly transforming too. The early crust stabilized. Continents began to grow larger through volcanic activity, and the first sediments started to form, muddy layers laid down by rivers and tides. These rocks became the first geological record keepers of biological activity. Tiny isotopic signatures, subtle changes in mineral composition, clues that something alive was influencing the planet's chemistry, even if no fossil could yet capture its shape. If this sounds uneventful, that's because it was. The Quiet Ages were not marked by drama, but by endurance. It was the universe's longest act of patience, a story without spectacle but filled with quiet triumphs. Each microbe that survived a thermal vent or acid bath was a victory against entropy. Each cell division was an act of defiance against decay. Life was still fragile, but it was stubborn, and that stubbornness would become its defining trait. From a human perspective, hundreds of millions of years of near-invisible progress sounds like an eternity. But in geological time, it was the blink before the sunrise. The groundwork was being laid for everything that would follow: the oxygenation of the atmosphere, the rise of complex cells, and eventually multicellular life. The planet might have looked like it was napping, but in truth it was dreaming. Dreaming of forests, coral reefs, and creatures that would one day look back and ask where it all began. Beneath its calm surface, in the quiet darkness, the machinery of evolution was clicking into place, one molecule at a time. When Earth finally woke from this long nap, it would open its eyes to a completely different world, a world forever changed by the invisible labor of its smallest inhabitants. The Quiet Ages were not an intermission. They were the overture. For hundreds of millions of years, life had been busy but quiet, microscopic, modest, and allergic to fame. The world above might have seemed empty, but below the waves, tiny pioneers had been transforming the planet molecule by molecule. Then, something subtle yet monumental began to happen. Life started leaving fingerprints. Not fossils, not bones, those were eons away, but chemical marks, patterns etched into rocks and sediments, the earliest signs that living chemistry had begun reshaping a once indifferent planet. It started in whispers. The first fossils of life weren't bodies but ratios. Tiny imbalances in isotopes. Invisible to any eye but clear as day to future geologists with the right instruments. Living things, even primitive ones, prefer certain isotopes of elements like carbon, sulfur, and nitrogen because they're just a little easier to work with chemically. When microbes metabolized their food, be it hydrogen, methane, or iron, they subtly shifted those isotopic ratios. Over millions of years, those microscopic preferences built up in the rocks, marking them with a distinct chemical accent that only life could produce. These weren't isolated occurrences. Across ancient rocks now found in places like Greenland, Canada, and Australia, scientists have uncovered isotopic signatures dating back over 3.8 billion years. To the untrained eye, these rocks look utterly ordinary, gray, dense, and worn smooth by time. But locked within their structure is a record of living metabolism. It's as if the planet had begun keeping minutes of its own biological meeting, written not in words but in the elemental poetry of carbon. But the writing didn't stop there. Microbes soon began sculpting the landscape in other ways, changing the chemistry of oceans and air. Some formed thin mats on shallow seafloors, trapping sediment and binding it together with sticky secretions. These mats hardened over time, leaving behind layered structures called stromatolites. They're not much to look at, bumpy, dome-shaped mounds of rock, but they are among the oldest physical evidence of life on Earth. Ancient stromatolites, some over 3.5 billion years old, are like the planet's first selfies, frozen in stone. Each layer in a stromatolite tells a story. Microbes at the surface captured energy, originally from chemical reactions, later from sunlight, and produced organic matter. Sediment settled on top, and the next microbial layer grew over it. This slow, repetitive dance created rippling, laminated structures that built upward year after year. Even without knowing what microbes made them, the pattern itself screams life. Nature doesn't stack layers like that by accident. It takes something alive to choreograph that rhythm. These early microbial communities were remarkably efficient engineers. By pulling energy from their environment and altering the chemistry around them, they began to influence the entire planet's balance. Iron dissolved in the oceans reacted with oxygen produced by some of the earliest photosynthetic organisms, leaving behind rusty red bands of iron oxide in the rock record. These so-called banded iron formations, glimmering stripes of red and silver running through ancient stone, are another kind of biological graffiti, proof that life was already altering the chemistry of an entire planet long before anything with eyes existed to witness it. It's easy to underestimate how revolutionary this was. For billions of years before, Earth's processes had been purely physical: gravity, volcanism, erosion. Now, biology had entered the chat, and it began rewriting the rules. Rocks were no longer just cooled lava or compressed mud. They became archives of interaction between life and the environment. Each new deposit, each chemical anomaly, was a footnote in the story of existence. Time, for the first time, had context. If you could travel back and stand on one of those early shorelines, perhaps beside a shallow lagoon filled with microbial mats, you might not even realize you were looking at life. The world would still seem empty. No movement, no color, just the slow shimmer of water under a hazy, orange-tinted sky. But beneath the surface, those mats were buzzing with activity. Microbes were dividing, metabolizing, trading molecules, and occasionally dying, each action leaving behind chemical echoes that would outlast mountains. The scene would look still, but it would sound, on the molecular level, like a billion typewriters quietly clicking. As these traces accumulated, they began to form patterns that scientists billions of years later would use to reconstruct the early history of life. Certain rocks showed the telltale depletion of heavier carbon isotopes, evidence that living organisms had favored the lighter ones. Others contained sulfur isotope patterns that revealed microbial breathing through sulfate reduction, a process still used by bacteria in today's oxygen-free environments. In a sense, These patterns were the first biological languages, coded in the atoms themselves. These signatures also marked the beginning of Earth's self-awareness, though of course the planet didn't know it yet. The processes of weathering, sedimentation, and metamorphosis began preserving traces of its inhabitants. The story of life and the story of the planet became inseparable, their narratives braided together in rock and mineral. For the first time, biology and geology weren't just neighbors, they were collaborators. And yet, these marks of life were fragile. Many were erased by time, buried beneath newer layers, or melted back into magma by tectonic churn. What survives today is a fraction of a fraction, scattered relics of the first written pages in Earth's diary. Still, they are enough to prove that by 4 billion years ago, life wasn't just a chemical curiosity. It was a planetary force. Think of it this way. Before this chapter, Earth existed, but it didn't remember. There were no records, no continuity. But once microbes began leaving chemical fossils, time itself gained memory. Every isotope imbalance, every layered stromatolite, every band of rust-red iron became part of the world's autobiography. The rocks, silent as they seem, are still speaking. They tell of a time when life's only goal was to persist, and yet, by doing so, it began to write. The handwriting was crude, the grammar entirely molecular, but the message was profound. I am here. And once that message appeared, it never stopped. From those first whispers in stone, Earth's diary would grow into an epic saga of change, catastrophe, and creation. But every grand tale needs its first line, and this was ours, written not in ink, but in the chemistry of existence itself. After billions of years of tantrums, eruptions, and chemical chaos, Earth finally began to calm down. The scars of its fiery youth were still visible, but the planet was no longer a raging furnace. The crust had thickened and strengthened. Volcanoes still grumbled, but they no longer blanketed the sky in endless ash. The oceans, those restless basins of steam and acid that had once boiled under a choking atmosphere, now stretched wide and deep, shimmering under the softening light of a maturing sun. Earth was, at last, settling into itself. By this point, around 3 billion years ago, the planet had begun to look surprisingly familiar. Continents had started to assemble, patches of granitic crust rising above the sea like the first timid islands of a world learning balance. These early land masses were small and scattered, but they represented something revolutionary: permanence. Before this, land had been fleeting, constantly destroyed and remade by the planet's inner heat. Now, tectonic plates had begun their slow, deliberate waltz, drifting, colliding, and recycling the crust in a pattern that would continue for billions of years to come. The continents of that era were barren, no plants, no soil, no life to paint them green. They were sculpted instead by wind, rain, and the relentless assault of waves. Weathering had become a new planetary artist. As the atmosphere stabilized and rain continued its eternal cycle, rivers carved into the raw rock, carrying minerals back into the sea. Sediments gathered at coastlines, building layers that would one day become the pages of the planet's geological history. The land was harsh, yes, but it was also beginning to mature, a planet transforming from molten metal into marble and clay. Meanwhile, the atmosphere itself was undergoing a quiet revolution. Volcanic gases still poured into the sky, but the balance was shifting. Carbon dioxide levels were high, maintaining a warm climate despite a sun that shone dimmer than it does today. Nitrogen became the dominant gas, while methane and ammonia, the old poisonous holdovers of the Hadean, were gradually being consumed by new chemical processes. The planet was becoming less toxic and more temperate, one slow reaction at a time. And beneath the waves, life was thriving in ways invisible to the surface. Microbes had mastered survival. They had diversified, adapted, and colonized every environment they could find, from the dark abyssal plains of the seafloor to the sunlit shallows near volcanic shores. Some microbes fed on sulfur, some on iron, and others on carbon compounds, creating a complex web of chemical relationships that made the oceans hum with unseen energy. Life had woven itself into the planet's chemistry so completely that the two could no longer be separated. Then, around this time, an extraordinary innovation began to reshape the future: photosynthesis. Certain microbes, ancestors of modern cyanobacteria, developed the ability to capture sunlight and use it to split water molecules, releasing oxygen as a byproduct. It was the biological equivalent of inventing fire, but on a planetary scale. For the first time, life could harvest the nearly limitless energy of the sun directly. The process was elegant, efficient, and incredibly disruptive. Oxygen, that reactive troublemaker, began to accumulate in the oceans, where it combined with dissolved iron to form vast deposits of rust-red minerals. At first, this oxygen didn't make it into the atmosphere. It was busy oxidizing everything it could find: iron, sulfur, even methane. But eventually, the planet's sinks filled up, and free oxygen began to leak into the air. The atmosphere slowly transformed from suffocating to supportive, setting the stage for entirely new kinds of life. Earth was, in a sense, taking its first breath. The consequences were profound. Oxygen was toxic to many of the microbes that had ruled the planet until then, leading to mass die-offs. Yet for others, it was an opportunity. Oxygen was an incredibly powerful source of energy, and life forms that could tolerate or even use it gained a massive advantage. Evolution, once a slow simmer, began to bubble with new possibilities. The great oxygenation event was still on the horizon, but its fuse had already been lit. Above the surface, the planet was also undergoing a facelift. With tectonic plates in motion, continents began to merge and drift apart. Mountains rose and crumbled, and volcanic islands formed new chains across the oceans. The planet's crust, once static and molten, had become a living canvas, reshaped by internal motion. These movements helped regulate climate. When volcanoes erupted, they added carbon dioxide to the atmosphere, warming the planet. When mountains eroded, minerals drew carbon dioxide from the air, cooling it. This geological balancing act became Earth's thermostat, keeping temperatures within a range suitable for liquid water and for life. The skies, too, were changing. As volcanic haze thinned, sunlight began to pierce the atmosphere more easily, casting a true blue over the oceans for the first time. Clouds formed from evaporating water, white and soft instead of dark and acrid. The air, though still unbreathable for humans, was no longer the suffocating fog of poison it once had been. The weather grew more predictable, the storms less apocalyptic. Earth's moods had softened. It was no longer an angry child of the cosmos, but a young adult planet learning composure. The beauty of this transformation lies in how slow and self-organizing it was. No external miracle intervened. No guiding hand rearranged the elements. The same laws of physics and chemistry that once melted the world were now fine-tuning it. The molten chaos had cooled into order. The once dead rock was now a dynamic, breathing system, a world with atmosphere, oceans, continents, and life, all intertwined in a delicate equilibrium. By the end of this chapter in Earth's story, the planet had achieved something profound: stability. It was no longer just a sphere of molten rock wrapped in gas. It was a self-regulating system, a planet capable of maintaining habitability over billions of years. It had found its rhythm, its heartbeat. Standing on one of those early continental shores, had there been anyone to stand, you'd have seen a world that finally looked like home. Blue oceans stretched to the horizon. The first continents glowed golden under a softer sun. The air shimmered with humidity, and the smell of minerals and salt filled the breeze. Life still hid beneath the surface, invisible and ancient, but its influence could be felt everywhere. Earth was ready. The stage was set, the air was clearing, and the oceans were teeming with promise. The molten world had become magnificent, not yet finished, not yet vibrant with forests and creatures, but steady enough for complexity to rise. The planet that once burned without mercy had learned something miraculous: how to endure. And endurance, as it turned out, was the secret ingredient to life's next great act. Before this moment, Earth had been a world of endless cycles: heat melting rock, rain wearing it down, volcanoes rebuilding it again. Time existed, of course, but it was meaningless without memory. There was no record, no evidence, no breadcrumb trail to follow. Then life began to leave marks. Not just chemical whispers, but physical ones. It was as though time, for the first time, had a reason to keep track. It started small, as most revolutions do. Microbes, those invisible founders of life, began to shape the world in ways that could be seen and, crucially, preserved. Layer by layer, they built structures in shallow waters, mats of living cells that trapped sediment, hardened, and grew anew atop the old. These were the stromatolites, living skyscrapers made of nothing but bacteria and patience. Each layer represented a day, a season, or perhaps a decade in the life of a microbial colony, capturing the rhythm of an ancient planet finding its tempo. They were not fossils of body, but fossils of behavior. Proof that life wasn't just existing anymore, it was interacting. Those layered mounds became the punctuation marks of early time. In a world that had previously erased itself every few million years, here were pages that stayed written. The sediments they trapped told stories of rising tides, shifting climates, and the slow thickening of the atmosphere. Each layer of rock became a kind of geological photograph, a snapshot of what the world looked like when those microbes were alive. It was as if Earth, through its living inhabitants, had finally invented memory. As oxygen levels crept upward, thanks to photosynthetic microbes tirelessly exhaling their waste gas, the chemistry of the oceans began to change dramatically. Iron dissolved in seawater reacted with that oxygen to form rust-colored minerals that sank to the seafloor. Over millions of years, these deposits layered into banded iron formations, glistening stripes of red and silver still visible in cliffs today. They weren't just rocks, they were signatures, each band marking a pulse in the rise and fall of oxygen, each ripple a note in Earth's growing symphony of time. The appearance of these records meant something fundamental had shifted. The planet was no longer just a place where events happened. It had become a place where events lasted. The past could now leave footprints for the future to find. With every mineral deposit and chemical pattern, the planet was writing its autobiography, and life was co-authoring every page. This was the dawn of what geologists call the rock record, the vast, layered archive that underlies our continents and mountains. In those layers, we find not just the remains of creatures long gone, but the story of climate, chemistry, and catastrophe. It's the closest thing we have to time made tangible. Without it, we'd know only the now. With it, we can trace an unbroken lineage from the first cells to the rise of civilizations. Of course, those early pages were fragile. The world was still restless, and tectonic forces had no respect for history. Many of the oldest records were swallowed, melted, or transformed beyond recognition by heat and pressure. What remains today are fragments, crumbled paragraphs of an epic that once stretched across oceans. Geologists spend their lives deciphering these scraps, teasing meaning from mineral patterns and isotope ratios, trying to hear the echo of that first voice that spoke through stone. But even with its gaps, the story is unmistakable. Time had found its anchor in the record of life. Sediment piled upon sediment, marking seasons, floods, and droughts. Microbial mats grew, died, and fossilized. Oxygen levels fluctuated, leaving chemical signatures in the strata. Each new event layered over the last, not erasing it, but preserving it in compressed whispers. Earth had become a historian, its crust a library bound in basalt and sandstone. As time marched on, these natural archives grew more complex. Life diversified, and with it, the records. Microbes began forming colonies that altered their environments, leaving mineral deposits shaped by their activity. Tiny filaments of microbial cells became entombed in rock, some of which survive even now as microscopic fossils. Their shapes, thread-like, spiral, or clustered, look deceptively delicate. Yet they've outlasted mountains. They are the first portraits of life, drawn not with ink, but with carbon and patience. What's remarkable is how these ancient traces connect us directly to the beginning of biological timekeeping. Every fossil, every stratum, every isotope ratio is part of the same inheritance. When we drill into a rock formation that's 3.5 billion years old and find the carbon signature of photosynthetic life, we're not just finding evidence of the past. We're reading a page written by our distant microbial ancestors. The story hasn't stopped being written, We've just learned how to read it, and that reading changes everything. For the first time, the planet had cause and consequence. The formation of a mineral or the layering of sediment could be linked to something living. Suddenly, time wasn't an endless loop. It was a progression. The planet had direction. The story of before and after had begun. From then on, every new chapter would build upon the last. Continents rising, climates shifting, species emerging and vanishing. The diary of Earth was no longer a rough sketch of elements and eruptions. It was becoming an epic, one that connected chemistry to consciousness. The writing tools were rock, water, and biology, and the ink was everything that had ever lived. Billions of years later, humans would come along, curious little descendants of that first biochemical revolution, and learn to read those marks. We would dig into cliffs and seabeds, translate the language of carbon isotopes and mineral bands, and realize that we were not separate from the story. We were part of its unfolding. When the first trace of life left its mark, time became more than a measure. It became a memory. The universe had been happening for eons, but only here on this restless blue planet did it begin to keep a diary. Every grain of sand, every fossilized ripple, every preserved shell is a reminder that we are living in the margins of that same book. One still being written, line by the only planet we know that remembers.